Welcome back. Welcome to the most hated show on the internet, but we don't stop, we don't quit. So here we are for a pretty fun, informative show. But before we get to all that, you already know. Wait for it. Where we at? Yeah, that part. So, what up, Anthony? How you doing?
Just chilling, sis. How about yourself?
Yeah.
That's what's up. What's up.
Doing good. Everything's lovely. I won't complain. So, yeah.
Nah, can't do too much complaining.
No, right. Can't do too much complaining.
It's been a good week, so.
It's been a really good week for me, so I ain't even tripping. Yeah. A really good week. But we about to get into it. So we're gonna introduce a couple things. I'm feeling like, what up, Barrick? Right on time. Hey, how you doing, fam?
How's it going? I was racing back from the gym to make it on time.
You good? Ain't no rush. You join when you want to. You know, we got the intro and we got stuff till we get into the nitty gritty.
Yeah.
But speaking of the nitty gritty, yeah. So it's pretty much we're going to be talking about the cosmic distance ladder. We're going to discuss a little bit about the Hubble constant. I'll talk a little bit about some key players, 3 of them in particular. Okay, because I think a lot of people don't know that it's just not Hubble. There was somebody else that they normally don't tell you about that was part of that work too. So we'll just shout out his name, George Latimer. We'll just shout out his name a little bit. Yeah, he was a priest and an astronomer, but you know, he was a part of that discovery. And we're gonna talk about I'm gonna mess her name, Henrietta Leavitt. Okay, a women. Shoot, I don't know if you actually. Well, I would. She is definitely considered. She was one of the computers at the Harvard Observatory back in the early 1900s, and her work set the foundation for what we call Hubble's constant today. So we'll get into a little bit of that. Hubble's constant, the cosmic distance ladder. I'm going to tell you a little about Cepheids. You can pronounce that 2 ways: Cepheids or Cepheids. Either one is okay. Okay. Yeah, we're going to talk about that. I think I'm going to add in a little bit about a particular type of supernova that's also considered what they call a mile marker.
Standard candles.
Standard candles, facts, yardsticks, all those terms in the play. I have to think of the Magellanic Cloud. I think we discussed that. I think that has some pretty interesting history. A couple of these things we'll probably go back over and do more in depth because they're all very in depth or whatnot. But just to give you a gist of what it means when people say the Hubble constant or the cosmic distant ladder, what does that mean? So that's what we're going to get into today. But before we get started, yeah.
You know, what you just stated, them last couple of phrases, you know, that we can make that mess around and get about 5 shows out of it.
Facts.
You know what I'm saying? Because what we're presenting tonight, the 3 main aspects of it is more like an overview. And when you dig into it, those three main aspects, you can make, like I say, several shows out of it. Because when you get to talking about the variables, there's different types of variables.
Facts.
You know, there's a lot of what they call rungs on or steps on the distance ladder.
Right.
And what we're gonna do is help you guys understand how we get these measurements that we're always talking about. Something that's so many light years away, and you know, these things. And this is how they do it. And this is the method that they use, which is tried and true. You know, but it comes from decades of adding to and refining the techniques. You know what I'm saying? So this is not something that someone was sitting up in a room and thought of, hey, let's do this. No, you know, there's different steps in forming this method. And it's like I said, it's tried and true once you get an understanding of it. And a lot of this stuff may sound familiar to some of y'all, you know, depending on how well you've retained a lot of the information that we've given. But a lot of this will be, you know, something or familiar. You know, there'll be some words or, you know, that we use, some phrases that you've heard us speak on before. So yeah, it's pretty interesting how they do it. And, you know, I hope y'all can get something out of it, a little bit of understanding.
Yeah, Anthony, and when I was researching it, I had at least heard on 3 or 4 occasions where the people talking about it said that they were surprised how people in earlier times got measurements so accurate.
Yeah, it's deep. And, you know, it's, like I said, there's steps to it. And it was, you know, in the early, well, I can't remember exactly what year, but those first steps are the foundation, and they really, you know, it's really simple, you know, using parallax, how they did it, but that can only get you so far. So that's where, you know, we come in and the generations behind them to take what they had and add to it and make it better. You know, that's what we should be doing if we're scientifically literate and, you know, we're living off of science. That's our operating system. Well, we know and understand that we have to take that information and refine it, make it better, or if need be, throw it out and start over from scratch. But you got to have somewhere to start. And those guys in the early days, they, especially, you know, using their parallax and understanding Newton's laws and all that good stuff, you know, it has become, like I said, a very viable method of obtaining distance.
Yeah, and they were also saying that, you know, each rung on the ladder builds or has to do with the one before it and above it, and like they're still actually working on it.
Yeah, that's what I'm saying. It's a great method that they put together. So if y'all ready, we can jump right in.
No, you got to do the shout out first.
I'm tripping. And we got the space forecast too, don't it?
Yeah. Sure do.
All right, let's get these shout outs going. Let's see who we got in here. Brother Smalls, peace to you. Gary Hart, what's happening, bro? I ain't seen you in a minute. Hope everything been good with you. Scarab Chronicles, appreciate you for joining us as always. Miss Bennett, #1 fan of the PseudoKillas. Appreciate you.
She a lady killer, so you know.
Lady killer, and most definitely. And who else we got in here? All right, that's it for now in the chat. But yeah, we appreciate y'all joining in. And
you got Scared always.
So
Yeah, peace to the chat. I'm not touching any more buttons because I tried to do something a second ago and I got kicked out, so I'm not touching anything.
That's funny. It's gonna do that. That's funny.
Most definitely.
Did you get Scarab Chronicles in there?
Yeah, I got Scarab Chronicles.
We got Gary and Smalls that just hit the stage. Unless
Yeah, I got
I'm still
Gary.
on this and okay, my bad.
Yeah, I got both of them, Smalls and Gary. Yeah.
Oh, my bad. Then hi. Yeah, so that's what we're about to get into today for y'all. With our special guest, co-host Barrick. Barrick is in the building. But
yeah. So from our were you gonna get started or
not yet.
Okay.
Uh-huh. All
peace,
right.
Shalem Way. Peace, peace,
dang.
my brother. Peace.
I can't even use that part. I messed up. All right. I'm gonna skip one section, but Anthony,
Mm-hmm.
you up? It's the space forecast.
I'm waiting on the music. I ain't realized the music has stopped.
Oh my God.
I'm sorry, y'all.
Oh man, that music is done playing. It'd be like quick 1, 2, 3, go.
Yeah, peace to you, Phi Tame. Appreciate you showing up. So this week, actually tonight, well, speaking on the space forecast, we're in for a treat tonight. There will be, you'll be able to see, with the naked eye, you'll be able to see at least 3 planets in the sky tonight, starting with Saturn, which should be rising right about now. If y'all got y'all Stellarium apps or whatever astronomy app you have, you can follow along with me on it. But if you scroll to the east, you'll see Saturn is just starting to rise. And I want to say Jupiter is going to come up maybe about, it'll be a lot later, about 3, 4 in the morning, along with Mars. Mars won't be too far behind it. So that's a nice little treat. You can at least see those 3 planets. Now, if you got a telescope, you should be able to see Neptune as well, right after Jupiter rises. As far as, I don't think there's any meteor showers tonight. I hadn't heard of any. So we won't, that's not going on. But, that'll be the main thing, other than, what we talked about last week. You with the telescope, there are plenty of objects you can see. You can definitely see Sagittarius is prominent at the at meridian, which is at its highest point. So you should be able to see a lot going on in Sagittarius if you have a telescope or some binoculars. The Eagle Nebula, a lot of different star clusters, and as we talked about all the time, Ms. Juju brought to our attention about Sagittarius A star, which you can't actually see it, but with a telescope you can look at that region and just.
You mean the black hole?
Yeah, Sagittarius A star, the supermassive black hole of the Milky Way. Our supermassive black hole. That's where it lies in in the constellation of Sagittarius, which, like I said, looking towards the south and up, you should see, looks like a little teapot or coffee pot, but that's Sagittarius, and that's where our supermassive black hole lies. So with the telescope, you can actually look at the region. You won't be able to make out a black hole, Of course, you can't see it, but looking at the region is pretty cool. You can always find the Big Dipper. You know, there's a lot going on around the Big Dipper. It's setting now, but it never really fully sets. And there are some objects like M81 and M82, which are two interacting galaxies you can see with a telescope. They never set, so you can always see them all year round, but they make for a good sight through a telescope or some binoculars.
Right.
Andromeda will be rising around about 10:30 maybe in the east, northeast a little bit. So if you got some dark skies, that's one you can see with the naked eye. Now, you won't see any spiral arms or anything. You'll see a fuzzy patch in the sky. But once you see it, you will automatically know that's not a star. You know, it's something else. So that's pretty dope. That's pretty much, you know, all we'll get with, you know, just naked eye or with a visual telescope, small telescope. Most of the other objects, you know, you're going to need something pretty big. So we won't really get into those. But yeah, if you got that app or any app, you can follow along, like I said, with the night sky as it moves and what's all out there to see. You know, there's a lot of globular clusters and open star clusters around Sagittarius, because that is an actual arm plus the center. There's in the center of our galaxy, they call it a barred spiral. So there's a bar with two big spirals coming off those bars with some spurs in between. So when you looking at Sagittarius, you're looking at the center of the galaxy and that bar. So there's, the stars are immense. There's so many big, bright stars. And what makes that, well, it's kind of a hindrance. It's a good thing and a curse. Because, you know, that part, looking at that part of the Milky Way, we can't see on the other side. Right. Because all the dust and stuff blocks the light from the other side of the galaxy. You know what I'm saying? So it gives us a blind spot, but at the same time, it's a lot going on there, you know. So if you get a chance, get your binoculars, look to the south and up towards the equatorial plane, which is the plane that the planets and the moon moves on. Mm-hmm. You look towards that, you're in for a treat. You're in for a treat. So that's all I got for this week on the space forecast. But, you know, tune in next week and I'll have something else for you.
We'll have some more. So I wasn't going to do it, but I'm going to let y'all on the joke. So just don't. Yeah. I messed up. It's okay. I've been busy. Okay. But here we go. So just imagine that's said instead of spectroscopy, it's said like the cosmic distance ladder, the Hubble constant. Mm-hmm. Yeah. And then Cepheid variables and other things.
Hey, we all good.
Yeah, I was like, and I just realized that I did that. Sorry. I be doing so much sometimes. Yeah, I was on a roll when I put that together. I ain't even remember I did it.
Yeah, see, we got a few more than popped in.
Yeah. Shout out, fam. Thank you.
Shout out to Miss Choco Kitty. Shout out to you. Appreciate you. And Ramon Berry. Mm-hmm. Appreciate you showing up as always, fam. Appreciate you.
Facts.
Sorry about that, Miss Juju.
No, and Fontaine. I gotta say that. I said that before, but you know, just so everybody can hear, you know, don't want to forget family. For sure. So, like always, I don't ever go in no type of linear direction or straight line. I kind of put pieces together. But I thought I wanted to have something fun with you all. So I think we'll do a little bit of math classes. We're going to do a little fun math quiz. I'll buy lunch. It's a $25 lunch, okay? So if you want to grab paper, a calculator, and a pencil or a pen or something to write with, I'm gonna give you some stuff, and then I'm gonna ask you to calculate some stuff. You ain't got to be approximate, but I'll just, like we gonna test the science ourselves to see if they, you feel me, they hanging in there, right? You feel me? Or we gonna have to talk to these people. So where will I like to start at? Shoot, did I already forget what I was gonna do? Nah. Okay. Shoot, get nervous and forget everything. Nah, I ain't nervous, y'all. So I'll start. Shoot, should I make it easy? Okay. I'll start with the, if you're ready, wait a minute. I'll give y'all a few minutes. You need to play a little music. Grab your pen, paper, and a calculator. I want to have a little fun for about 10 minutes. You feel me?
Let's get
this done. If you're ready, like type ready in the chat. You feel me? I need at least 2-3 people to participate. I got $25 lunch. I'm always good for the lunch. This ain't this is like this for real, this truth. So I'm gonna play like 2 seconds of music while y'all go get ready. And then I'll just get ready. I was ready. A little math. Not hard. People talk about astronomical units and parsecs, measurements they use to calculate distance and time. So people learn something. Once you learn this, you'll be able to apply it when you hear it or see it. It's great too. What is a parsec mean? I feel like we'll put that down. There's an astronomical unit and then there's a parsec. All of them are considered like astronomical units. Yeah, I thought we would have a little fun with that. Oh, I got one ready. Thank you. Anybody else? Shout out Keenan. Send me light and love.
Peace, Keenan. Lamar, peace to you.
Get one more player. Then we're gonna get your car time. Okay. We'll have fun.
Okay, we got two.
I got two. We're gonna get 3. Hello? One more person. One more. 3 more minutes. $25 lunch card. It's on the time. It's easy. It ain't nothing crazy, y'all. I can do it. I can do it. Okay. Well, Gina, Chilembwe, or whoever else, y'all can jump in when I want. So I'm going to give you some figures, okay? So if you don't know, I'll start easy for y'all. A light year is 5.88. Is 5.88 million years. Excuse me, trillion miles. Messing that up. 5.88 trillion miles. I'll start with that first. Light year, 5.88 trillion miles. Then you have a parsec. So astrophysics, astronomers will use parsecs and astronomical units, and I'll get to that, to make the calculations where they're not so big, because the distance and the time, which is one and the same when you get in astronomy, is so much that they had to find a way to contract it a bit so it wouldn't be so crazy, because we're talking about trillion. You know what I'm saying?
That's a lot of zeros.
A lot of zeros.
And
so
a lot of numbers to carry. You know what I'm saying?
Yeah,
You're trying
exactly. So they figured out a way to bring it together. So I got that 5.88 trillion years. That is
trillion miles.
Light year. Trillion miles. Got it. Yeah, years, miles, distance, time, same thing. But anyway, 5.88 trillion miles. That's why I messed up, because I've been studying the parsecs. Now, parsecs, this is your second thing. This is 3.2926 light years. So parsec is 3.26 light years. Okay? So I have 1 light year, which is 5.88 trillion miles. And then I have 1 parsec, which is 3.26 light years. Okay? You got that? Now, give you an astronomical unit. So an astronomical unit is 200,000. It's 206,000. 265. 206,000 and 265 astronomical units. 206,265 astronomical units. That's 1 astronomical unit.
No, the astronomical unit is 93 million miles.
Wait. I got this. I had this so good when I practiced. I messed up. So astronomical unit is actually 19.2 trillion miles, and it's 30.9 trillion kilometers.
Wait a minute. The astronomical unit is the distance from the Earth to the sun. So that's 93 million miles. Now, I think what you're saying is there are 2,000 plus astronomical units in a parsec.
Yes.
Yeah.
That's what I'm saying.
I'm with you.
Yeah, don't mess me up. Don't cut in because you'll make me more confused. But
no, what I'm saying is the astronomical unit. See, you said an astronomical unit is this, and it is this many astronomical units. You know what I'm saying? The astronomical unit.
Parsec. So I'm doing parsec, light years, parsecs, astronomical units.
The astronomical unit is the smaller of the number.
Right, but I'm doing it for 3.23. I mean, 3.
You're doing it for a parsec.
Yes, that's what I said. Parsec. I'm doing light year, parsec, and astronomical units. That's what I said. Don't change it. This is not. I'm sorry. It's not 1 astronomical units. It's the number of astronomical units in 1 light year. I was gonna get to it. I'm gonna self-correct. Don't worry. I'm gonna get to it. Shoot, the numbers be tricky though. But if you're with me, tell me you're with me. Okay. So let's do it. Let's go through it one more time because I don't want to confuse me or Anthony or y'all. So we got 1 light year. It's 5.88 trillion miles. Then we got 1 parsec, which is 3.26 light years, y'all. And 1 parsec is 206,265 light year. I mean parsecs. Okay. Astronomical units.
Yeah.
But that's
you're right. Keep going.
See, Anthony, it was better when I did it by myself, I swear. In those 206,265 astronomical units, that equates to 30.9 trillion kilometers. I'm not gonna mess with that, y'all, but just in case you want to, look smart in front of somebody and you can tell them, you feel me, how many astronomical units that number is, which is the number of a parsec, okay? And then you have 19.2 trillion miles. I might use that, which is also in the number of a parsec, okay? Are we clear? We clear, Anthony? Is everybody else clear? Did we mess that up too bad? Y'all good with that?
You good.
Okay. So I'm gonna give y'all an easy question. So I want to see if you can measure like 4.2 light years. Can you give that to me? No, I'm gonna do that wrong. I'm gonna hold up with that. I was gonna ask y'all to tell me. I ain't gonna make it hard. I ain't gonna make it hard. Tell me how many light years is 19.2 trillion miles? What you laughing at, Anthony?
Because you're trying to jack them up. There's a lot of numbers. I can see them calculators burning up right now.
It's not. That's easy.
Yeah, it is. It is.
What was the question I asked Anthony?
Huh?
How many light years is in 19.2 trillion miles?
Yeah, that's a good way to ask it.
Okay.
But you're looking at, yeah, that's a good way to ask it. I mean, I could tell you, but I want them to answer. You're almost right, Gina. Not quite.
What she got?
3.26. That's one light year.
Close. You close.
Yep, she almost there. Miss Bennett got 6. I think that's your answer, right?
That's really good, Miss Bennett.
Yeah. Because see, what you need to do is divide 3.26 into
Correct.
19, or divide 19 by a light year, which is 3.26.
Correct.
And that'll give you your answer.
That will. She got it. She pretty much got it, though.
But I think she wanted them. She be paying attention.
She do. She do.
We got to watch her. We're going to have to make the contest. She can't be eligible for the contest.
Yes, she can. 19.2 miles is one parsec, and 1 parsec is 3.2. 3.62 light years. No, a parsec is 3.
Yeah, the part. She's right about the parsec.
Yeah, but parsec is 3.2 light years. One light year is 5.88 trillion miles. Calculating's hot.
So what you need to do, Scarab, is see the 19.2 trillion miles. That would be 6 parsecs, because 1 parsec is 3.26
I said it wrong
light
1,000 times. I may do another one in the end, so wait on it. But go ahead, Anthony. Do that. You would divide it.
Yeah. So what you would do is divide the light year, the number for the light years, into the miles. Or you can convert, because if you convert the light year into miles, it would be 5.88 trillion miles. So if that was the case, then you would multiply, you know what I'm saying, or either divide 19 trillion by 5.88 trillion.
Correct.
And that's how you would get the answer.
That's the way I did it.
Yeah.
Yeah. Well, you know what to do. You need to go ahead and send me your Cash App. I probably already got it, Valisa, so I can send you lunch money. Gary, you ain't have an answer to that? I'm messing with Gary. So
no, you had me messed up on the 265. I was trying to write it down.
I fixed that though.
That was all messed up.
I fixed that though. It's an astronomical unit. So that's how many astronomical units is in 3.26 light years. I should have said it like that. Or in 1 parsec.
Mm-hmm. Yeah.
Are you clear now? Is everybody clear? So we were going, so a light year is one thing, that's 5.88 trillion miles, but a parsec is 3.26 light years, which is 5.88 trillion miles times 3, pretty much.
Yeah, pretty much.
Okay, so that's how you would do that. Y'all figured out? So yeah, that's how you, and so that astronomical unit is the astronomical unit for that 3.26 for that parsec, which is a combination of light years, would be the 206,265 astronomical units, which will equal to 30.9 trillion kilometers, equaling to 19.2 trillion miles.
Yeah.
Because time and distance is the same in space. So however long it takes you to get there is however many years it is away also. Doing this so people can also have a conceptualization on the magnitude of the space and time that we call the universe.
And the vastness of it. I mean,
the vastness of it.
Just think about it like this. You
Don't do
traveling
me,
to
Felicia.
your favorite destination. That's
Don't
no
do me,
more.
Felicia.
That's no more than, a few hundred miles. Now imagine trying to travel a parsec. You're gonna run out of gas. I promise you. That's a long way. I mean, whoo, 5 trillion miles, man. That's a lot of moving, a lot of space to cover. So that's why it's not so easy to get to Mars or to other planets. It's not easy. It takes months. So if you're talking about traveling along this distance ladder, you can forget about it. You can only try to visualize it and use your telescopes to measure the redshift in these objects to try to get a great or an accurate assessment of the distance, because you're not going to travel there. Voyager has been traveling since the late 70s, and it still hadn't left the solar system. So it's been traveling since 77, I think, 1977. That's almost 50 years, and it still hadn't left the solar system. So it's a lot of space out there to cover. Yeah. So with that said, congratulations, Miss Bennett, on that. I hope y'all got a good understanding. But that's a lot of distance to cover, and that's what we're going to be talking about in this series, is how they measure those distances.
Facts. I'm gonna blame Anthony for the confusion because I'm self-correcting. You feel me? So I'm just gonna blame him.
I'll take that.
I have no problems getting it before, but yeah, it is confusing. But I still wanted you all to get the rate. So we know what a light year is. It's 5.88 million. Trillion miles. And then you need 1 parsec is like 3 and something of them light years. So you will have to times that to get the millions of miles. But yeah, that shows you the vastness. We're dealing in trillions and billions and a whole bunch of other stuff. And then when it goes to other units, it's like mega kilo or kilometers, mega kilometers. I'm just like, what?
Yeah. And you're correct on that, Scarab. Well, yeah, that's correct, Scarab Chronicles. 1 parsec is 206,000.
That's why I put it on the
265 astronomical units. Yes.
That's why I put it on the screen. But Valicia, I will shut you out. You got lunch for tomorrow, so I'll get that to you by the end of the show. Thank y'all for participating. We'll do it again. I have it better, but we're gonna do that. We're gonna at least learn parsecs. I think that's important to learn because that's something like easily understandable, and astronomical units. I think we can place that now. And if y'all got it, wait, because I might do another one at the end of the show, okay? Or towards the end of the show. And we'll do it a little differently. So
yeah.
So
but that was pretty good there, Miss Juju. You got them with their thinking caps on.
Yeah, because I need to think. I need to figure, you know what I'm saying? It helps you conceptualize what these people were doing, especially Edwin Hubble. You feel me? And the magnitude of the work. It also, I think I'm gonna start with her. It also helps you understand the magnitude of the work of this woman, because I'm gonna start here first, because she was a calculator. Remember we talked about the human calculators? We know about them. particularly about the African American women, because they weren't given their proper credit ever. And I will say she wasn't either. She wasn't nominated for a Nobel Peace Prize when she should have. And when they decided that they would nominate her, she was like, she passed away 3 years before that of cancer. Kind of wild. So
Hey, you
they
know what else crazy about that, Miss Juju? Back then, astronomers didn't really get the recognition that they should have, because you know
Mhm.
Hubble doesn't even have a Nobel Peace Prize. I don't think they've given him one. I know he didn't get one when he was living.
Gotcha.
But
And they don't give them that post word. What is it?
yeah, post mortem, is that what they call it?
Postmortemly or postmortuously.
Yeah.
They don't give them that, and that was said in the article. But what is awesome about her? So let's start with them. The Hubble constant is like the constant rate or the expansion of the universe. And so all these things do several things at once, right? So you get a wealth of information about, you know, about different things, attempting to study one thing. And we'll get into why they even were studying this. And oh my God, I learned a lot. So when we talk about the Hubble constant, this, this rate of the expansion of the universe, but then you have the cosmic distant ladder. We talked about that. So the cosmic distant ladder is important because it's a series of measurements of different kinds of what you say galactical or astronomical objects with intrinsic brightness. So that means that these objects have some sort of light emitting from them, right? And because of this, researchers can use this to calculate distances. All right. And so some of the things that are important in this and that they realized in the early 1900 are the Cepheid stars. Okay. They're considered like, they call them the cosmic yardsticks. Okay. And then you have some other figures that are known as certain Cepheids are known as what they say. You said it earlier, candle lights,
Standard candles.
standard candles. And then you have a certain type of nova. It's a 1A supernova. And this is considered a mile marker. And all these are, you know, points. Like you're on a highway, you're on a galactical highway, and you got the sign with the distance, then you have the mile markers. Yeah, this is what it's doing. It's building up to a destination. And then they calculate, from the earth, the destination to this object, and then from that object to the next object, and then from that object to the next object. And they're just building this ladder of measurement for the distance of these objects, which essentially measures the distance of the universe, which becomes the age of the universe. And that's when we got a roundabout age, but we know that Hubble wasn't quite correct. He had an approximate, and it was a big one. I think he had it between 10 billion or 15 billion and 20 billion years. Since then, they corrected the measurement and we got it to a more accurate stance. I just want to say that 10 to 20 billion years, yeah. But without the work of the lady posted, that would not have happened in the time it did. Okay.
Yeah.
So
She was pretty deep.
Henrietta Leavitt. So what Henrietta Leavitt did, which was pretty awesome, is she actually figured out that there was a variability rate. Well, let me get into it because this is also gonna be our scientist of the week. I will get back into that a little bit, but then we can also learn what she did. It's her thing is called the period luminosity relationship. And they call this Leavitt's law now. That's what she brought to the field of astrophysics. During the time that she was considered a human computer at the Harvard Observatory School. But she was born in July 4th, 1868. And she was an American astronomer. Her discovery of how to effectively measure vast distances to remote galaxies led to a shift in the scale and understanding of the scale and the nature of the universe. Nomination of Leavitt for the Nobel Peace Prize had to be halted because of her death. I said that, but she graduated from Radcliffe College. She's from Massachusetts. I know that she comes from an English Puritan family. One of her descendants was a tailor that moved to Massachusetts. That's pretty much her lineage. She's also a Christian, and she was a devout Christian, and they say that in the work. But after she graduated from Radcliffe with the bachelor's, and I don't even think her bachelor's degree had anything to do with astrophysics in any form, but she ended up going to Harvard College Observatory, that's what it's called, to teach the women's portion. Okay, remember this is literally 1900. I think some of her foundings were like in the early 1900s, like 1901 or something like that. Okay, then Edwin Hubble came in like 1920s. Okay, but she was teaching as a human computer tasked with measuring photographic plates. So what's awesome, I was trying to say this earlier. So this was the early form of photography. So instead of having the early form of photography, they had photographic plates where they would use silver salts to capture images. The only thing about this, it didn't last long, and the silver salts were very sensitive to light. Okay, so and this is very kind of tedious to have these different plates and stuff. And the plates were consistent of like thin glass, so don't knock it. It's broke and then you lose it all. So I'm sure that was kind of stressful. I couldn't imagine. But she got this interest from a teacher astrophysicist that she wanted to help measure these different stars. So the photographic plates were to catalog the position and brightness of stars. So the work led her to discover the relation between luminosity and the period of Cepheid variables. So Leavitt's discovery provided astronomers with the first standard candle. So what is a standard candle real quick? On the cosmic distance ladder is a succession of methods by which astronomers determine the distance to celestial object. A direct distance measurement of an astronomical object is possible one for those objects that are close enough to Earth. Dang, it just didn't give me an outright straight definition for the standard candle. But the standard candle basically be those stars that they consider to have the most accurate variable in order to make the most accurate measurements. That's pretty much what a standard candle, because they took me on, they was going to have me read a whole another 1,000 paragraphs. So
well, you can a easy way to look at it, Miss Juju. I mean, it's the consistency of it. It's it's a standard.
That's what I said.
Yeah, it's the
most, yeah.
It
has the most consistent variable.
Yeah.
Yeah. So yeah, that's the period luminosity relationship, or what they call Leavitt's law. And that was basically her contribution to it. And then a few years later, here comes Edwin Hubble, and he literally used her work to calculate and come up with the Hubble constant. That's what he did. And the early measurements of the date of the universe. So I find that pretty amazing that happened. So shout out to Henrietta Leavitt for her work. And that was some good stuff. Did you want to add anything?
Yeah. So can I add on to that?
Yeah, go ahead, Gary.
Yeah. So when I was researching it, what I found was the first rung, or the first thing on the ladder that they use to find out like distances, is they'll shoot like laser or radio waves at a planet, and they'll take how long it takes to get back, and then with that they can figure out the distance for stuff that's in this galaxy, and then moving up to the next rung when you're looking at distant stars. That was the phalanx stage of it, where, like, say you take your hand and or your arm and you stick it straight out and you put your thumb up. If you close each eye, you notice how it shifts. So what astronomers did is say they would take a picture of the star and say January, and then 6 months later, when the orbit was exactly 180 degrees the other way, they would take a picture 6 months later, and then they would compare how that star changed based on the background stars.
Mm-hmm.
And based on that shift, they would be able to figure out what was called the phalanx angle. And then using trigonometry, they would figure out the distance. Then moving up to what you were just talking about, the third step would be like the standard candles, where they're taking the intrinsic constant, light of an object that's the same no matter what.
Yeah.
And by using the inverse square law, they can figure out the distance by using that. And I think one of the final ladders, or where they're at on top, is that's when they use redshift and the Hubble space. That's when they use the Hubble's law for like the final ladder. And that's what I found out when I researched. So hopefully I didn't mess anything up, but that's the information that I was able to come up with.
That's pretty awesome.
Yeah, that was pretty good, dude, to just start looking at. I mean, but it just shows you how simple it is. It's when we think about the universe and the cosmos, a lot of people get nervous. It's so much, yeah, it's a lot going on, but it's actually really simple once you get to learning what all these different things and the parameters of each one is. Like, okay, we speak about the variables. There's a few types. You have the Cepheid variables, which are pretty much field stars like our sun that goes through a periodic change. And they're pretty constant. Every way you look, they're pretty constant. So that's what makes them a standard candle, because they're pretty standard, throughout the the nearby universe, or our part of the cosmos. But being a single star, there's only so far that you can see a single star go off. You know what I'm saying? It's not going off in supernova, and so it's not getting as bright as the galaxy. So that's good for close by galaxies. I think the first one Hubble found was in Andromeda, and that let him know that Andromeda was outside of our Milky Way. Because at one point in time, they thought Andromeda was a nebula. It's actually called the Andromeda Nebula.
Right.
That's what it was named. So a lot
That
of
was
people.
a great debate.
Yeah, but it was those Cepheid variables that actually broke that wide open. And
Correct.
then you have.
It was called the Hubble variable one.
Yeah, and there's documentaries on this where they show where he marked it on his plates. Miss JuJu was just talking about those plates that they use, because they didn't have the cameras that we use today. They recorded everything on these plates.
Yeah.
So, and you can actually see where he marked that star as VAR. So he was able to use that thanks to Henrietta Leavitt's work.
Correct.
He was able to use that. And then when you get to talking about other variables, you have a RR Lyrae, which are mostly contained within globular clusters. And they're usually stars like, they're not as the biggest stars, but you know, they're, I forgot what they say between A and F. See, we need our Hertzsprung-Russell diagram for that. But
yeah, they brung him up in here too. Was it Ijnar Hertzsprung?
yeah,
It's EGNAR. Like, how do you pronounce that? But yeah, he's in this discussion too. Yeah, I thought that was pretty dope because this deals with stars also.
Yeah, exactly.
The luminosity of stars. So, you know, all these people who had, you know, their expertise or cornerstone with stars were definitely in the conversation, you know.
Yeah, exactly. So those are, you know, they're single stars. They're just going through changes. You know, they're basically like oscillating. You know, they'll get bright for a certain amount of time and then they'll dim back down. Then they'll get bright and dim back down. But like I was saying, you know, it's hard to see single stars, even with Hubble, that are not gravitationally lensed in galaxies, you know, that are millions of parsecs away. You know what I'm saying? So then that's when you get to the type 1A supernovas, because they're consistent. You know, we talked last week, I think it was last week or week before last, we were talking about the Chandrasekhar limit. You know, that's when a white dwarf is in a binary system with another star that has gone into its giant phase.
Ago?
Huh?
We talked about the Chandrasekhar limit about 4 months ago.
Oh, it's been that long? Ooh,
yes.
I'm sorry, y'all.
We talking about last week, a couple weeks ago.
My bad. I'm sorry.
Oh my goodness.
My calendar off. But
ooh, go ahead. I didn't mean, I'm like, what is he talking about?
But yeah, that's when you have a white dwarf and a companion star, sort of like Sirius and Sirius B. But the companion star to the white dwarf is going through its changes. So it's puffing up. And a lot of that material gets gravitationally attracted to the white dwarf. And once it reaches a certain limit, it's gonna explode. It's gonna blow up. So that's a type 1A supernova. That's not what we're waiting to see. That's just a straight nova between a white dwarf and another star. But a type 1A supernova is when the white dwarf is completely destroyed in the process. So those you can see in galaxies very far away, because when you have a supernova, the supernova normally outshines the galaxy itself, unless it's a quasar. But for the most part, well, we don't have any quasars in our local area, but you can see those type 1A supernova going off at a very far distance. So that's where the type 1A supernovas pick up where the Cepheid variables fall off. You know what I'm saying? So, right. And then once you get past that, you get into the redshift. And that's what, you know, the last time we had Dr. Farrar on, he really went into redshift with us. So that's one of the other ways that we use redshift. You know, we use it to get time and distance, like Miss Juju said a little while ago. They're one and the same. You can't have you can't have time without space. You know, that they're one and the same. Like I've said several times on this show, if you set your glass on the table and you walk away from it, you just created time and space between you and that glass or object or whatever it is. You just created time and space in between. So it's going to take you time to get back to it. And you're going to have to, that time you're going to be used to cover the space or the distance. So you can't have one without the other, you know. And those are the ways that we can measure the time and the distance, because we know the speed of light. That's a constant. We know what it is. And now we know how to use it or how to get it, the speed of objects, the direction they're moving in. We can understand all of that by understanding the distance ladder and the steps that make up the distance ladder.
Yeah, and Anthony, I wanted to add to your standard candle. Another standard candle that they said was that they use is a spiral galaxy. The faster it spins, the lighter it shines. So that's another type of candle that they use.
See, it's like I was telling Miss Juju. Yeah, this could be a series, you know, because it's a lot going on in there. I mean, we're giving you the basics of it, but we're gonna go deeper into each one of those rungs on the distance ladder. But that's pretty much the gist of it. But yeah, there's several. Well, I'm not gonna say several, but those what they call standard candles. You know, don't let that term confuse you. It's just a standard. You know, they've observed a lot of different. You know, they've observed objects all over the universe. They measure the light. That's where spectroscopy comes in. That's what we talked about last week, spectroscopy.
Exactly.
So, and that's how we can measure the red shift, the composition. That spectroscopy, man, we get a lot of information from the light, you know, from the light that we observe.
The elements that they have.
The
elements that different stars have.
Yeah. All of it.
Well, the picture on the where you finished, Anthony?
Yes, ma'am. Yes, ma'am.
So the picture on the screen, I don't know if I should just stop the show because you just pretty much went through it all. Shoot.
But that was the condensed version. Like I said,
I love it. I was like, all righty, I'm good to go.
We're gonna dig deeper into them because this is a very intriguing topic.
So it is. I like this one. This is a Hubble variable #1 star. There isn't like any great pictures, but it's located in Andromeda. Don't laugh at me, Valisa. And this is, I'm gonna tell you about the great debate. I thought this is wild. So the debate was the galaxy, the Milky Way galaxy was like it for the universe. There's you can't go past the limits of that. They also thought that Andromeda was like part of the Milky Way, and it was just like this spiral nebula. That's what they call it. So there's this big drama and argument over it, and all these debates and big papers, and I mean, it was like an actual debate too about it. I reckon for how I'm reading. But the thing is that they call the Hubble variable #1 probably one of the most important stars in astrophysics because it literally this whole Hubble constant and the distant and calculating the age of the universe, like that shook the world of astronomy. Figuring out that the Milky Way was just part of the universe and not the totality of it, and Andromeda was a whole galaxy, that shook the field of astrophysics then. Like shook it to its core. So when you talk about the Hubble constant and then the cosmic distant ladder, these like phenomenal things. But yeah, the Hubble variable #1, that's the correct name. I missed the number part. It's called the variable 1 for short, but this is Edwin Hubble's star, and this is what he used to calculate his you know, the major one to calculate his Hubble constant, besides other things. But this was his baby, this Cepheid star in the Andromeda galaxy. I brought up this picture because this shows you how they use the intrinsic brightness of these stars. Because you can see here, I think this is December 17th, the same star. Then go December 21st. It's a little bit lighter, if you all can see it. Let me see if I can blow it up just a little bit more. That's too much. And then it goes December 30th. It's even more brighter. Then January 26th is bright, bright. It's contrastly way different than what it was December 17th. That'd be a little over a month, like a month and 10 days. So what is like 40 days? I'm roughing it. If you want to correct me, I don't mind. But I just think that's phenomenal. I think this is a beautiful picture of Andromeda and the stars located in there. I don't even know if we'll get to the other stuff or we'll pick up on it next week, but I just want to share that. So that was a great read. Of course, the sources I'll let you have that about the great debate and all that led up to knowing what we know now. And even though, you know, Hubble didn't get it in there, he had the right idea. And so, you know, you had other astronomers that stood on his shoulders and were able to do that better. Thanks to Henrietta Leavitt. That's a nice star. And so now I bring you to this pretty awesome star. How did I miss that? Tell me. That's right. I'm going to show it to you because it's pretty. This is pretty amazing. What did I do? Wow. I just erased the whole page. But this star right here, this is a Cepheid. This is a Cepheid. Just to also show you the brightness and also the beauty on the things that they were using for their standard candles, for their yardsticks, their you know, and different things like that. But this is a Cepheid star. I can't give you the name of it because I lost the whole page. I'm tripping tonight. But when I find it, I'll give you the rest of the information on that Cepheid star. But I just wanted to show it to you because of the brightness of it. And it's beautiful. If I'm not mistaken, that one is in... I'm not going to say that. I wanted to say it was in the Magellanic Cloud. Did you want to add anything about the Hubble star or the Great Debate?
Well, it was. I mean, you covered it all pretty much, sis. I mean, it was like you said. It was a heated topic back then because you know during those times they thought.
Do you remember this star?
Huh?
Do you remember what this star is? I know you know it.
No, I can't remember it by name. But you know, back then, they thought everything was the Milky Way, and
Right,
it was that finding the Hubble variable one that
right.
proved that it couldn't be in the Milky Way. You know, it was too far. So that was a heated topic back in those days.
Yeah, I thought that was wild. I was like, oh wow, that's wild. I have a chart for you. I want to know. I'll come back to that one. Dang, that was an awesome picture. When I did the lady's face, it clicked it off. I like this chart. Um luminosity or magnitude, which is the same thing. We talked about these when we talked about characteristics of stars, in the period of variability, which is in by days. So as this goes, the luminosity gets um, higher, or excuse me, lower or brighter. So the lower the number, the brighter the luminosity. Like we always say that science is counterintuitive, and there is a lot of that in astrophysics. Okay, um, and I'll probably revisit some stuff about the characteristics and bring that back in also. But I thought this chart was pretty interesting, and it talks about the Cepheids or Cepheids and the large Magellanic cloud, which is a dwarf galaxy outside the Milky Way, and the ones in the Milky Way. Just basically measuring the difference. They realized that the band of Cepheids in the large Magellanic cloud were really bright and very useful to this. So they started to use those also, and then seeking out more. So I think once they realize about the Cepheids and how they can use them, then they start looking for them. So all through the 20th century, you have these discoveries of these Cepheids um, all the way around. But yeah, so this gives you the brightness here that's going vertically on your left hand side, and then at the bottom it gives you the number of days of variability. So uh, this is pretty awesome. And then where they located. Of course, the yellow ones are the Cepheids, and the blue ones. Cepheids in the Milky Way are the yellow ones, you'll see. And the blue ones are the one in the large Magellanic cloud, um, which I thought that was awesome.
And look at once again, Miss Juju, like we say all the time, you got you some good science, you'll come up with a very, very useful graph. You know what I'm saying?
Right.
Yeah. And it's this is an amazing tool, you know, but it's just that's what science does. It gives us understanding, you know,
Correct.
and you have to take these steps. And this is what the pseudo don't want to do. You you can't miss those steps. You know, there's a lot of steps that's going on. So yeah, that's pretty deep. That's a nice chart there you got, Miss Juju.
It's a dope chart, I think, because it just breaks down your luminosity of each star, calculating its brightness, and then at the same time telling you the days. So, um, Cepheids are interesting. When we go deeper into Cepheids, we'll explain like what's taking place that's causing these stars to be variable. What it means is like sometimes they're brighter than other times they're a little dimmer. Why is that happening? It's because this star is expanding and contracting over and over again. So to us, it looks like it's pulsating. That's what a Cepheid star is. A Cepheid star is literally in its own class of stars. When we dealt with the characteristics of stars, we didn't talk about Cepheids because they're in a separate class that's totally different. And then you got different types of Cepheids, like Anthony was saying. Some of them different um, have different variables in the same star, if that's what you call it. So they have one that's more constant than the other. So, the rate of the variable they can measure, right? So if it's like right 40 days or if it's right 50 days, they can measure all these things. And then they can measure that some of them have different cycles of this. Yeah, it was pretty deep and pretty interesting. Mm, I'm sorry I lost that screen, and I won't be able to find it now, but I'll bring it back next week with that.
Yeah, it's all good, sis. We'll, like we say, this is gonna be a series. So
Right.
we'll break down each one of them in more detail because there's a lot more, a whole lot more that goes along with it.
Tripping. So this is, I thought was another amazing picture, and we'll probably go through it again. But you basically can see the Milky Way in the middle. This is basically a cosmic map of, parts of the universe that we know, and it gives you the degrees of it's going out. So 0 degrees to 180, then it's 90 to 270 degrees with the width. So you see our slim. So now these point, if you look down from the top to the bottom, you'll see where it is placed, and you can calculate somewhat of the degrees because it goes in a circle. So you have the Milky Way here with this Sagittarius dwarf, and then over here you got the large Magellanic Cloud. Then you have the small one, and there's a neat story about that. So, and you can see the distance and see how they can use this to measure. And we'll go deeper. I don't think we'll get into the deep stuff, the Magellanic Clouds, but we just wanted to give you the opportunity to understand what the Hubble constant was, the cosmic distant ladder was, how that came to be, understanding distance and time, or space and time, and what that looks like, because I don't think that we really understand what space and time looks like. So that's pretty awesome. That's really all I have. I'll give y'all one more of the cosmic ladder. You have anything you want to add, Barrick?
No, I'm good.
Anthony?
Yeah, we pretty much summed it up, sis.
Okay.
It's a good introduction for sure.
Got it. Well, thank y'all for being here tonight. And yeah, I might come back with another question next week, but Valisa, Queen Valisa, I definitely got Lady Valisa, I got you on lunch. I'll send that to you in a little bit. You'll have it by morning, no doubt. So you can have for tomorrow. You want to do closing remarks, Anthony?
Yeah, I just want to thank everybody for showing up, giving us your time. Hopefully y'all can take this and become more scientifically literate, and well, y'all know by now, like I always say, when you're scientifically literate, they can't drag you down to that level and beat you up with experience. So y'all have a wonderful night.
Bye. Till next time.
Scott and cleared up for me just in time.